We are looking at equation of a line with vectors, so we do some of the same things that we looked at when we did equations of lines back in grade 10. In grade 10, and you were solving systems of equations with graphs, do you remember that two lines most often intersected at a single point? Okay? But sometimes they were parallel and never intersected, and sometimes they were exactly the same line and had an infinite amount of intersections. So, here's one possibility: they're parallel and distinct. In vectors, how do you, or in anything, how do you tell if two lines are parallel? Well, you set up your systems of equations and solve, and usually what happened was everything disappeared when you tried to solve, and you got a statement like 0 is equal to 0, or you got a statement that like 0 is equal to 5, something that can never happen. And so since you get something that can never happen, you know that the two lines can never intersect. So we want to show that the following two lines are parallel. Okay? A couple of things we could do. One, if I got a question like this that actually said that they're parallel, I might just start like this. Oops, not a fraction. I might start with the two direction vectors. Direction vectors are kind of your slopes. And say, is there a k value so that they're equal? Yes. K is equal to 2. So you could do that right away. It would be the easiest way to solve this question, to show that they're parallel. Since 3, 2, and 6, 4 are parallel,
Would I be able to borrow your pocket chart for period 2? Okay, thank you so much. Mine disintegrated.
Very good.
I will. Thank you.
But if you did want to solve a system of equations, then you would have to, right, you could go to the parametric equations. So the one equation is x equals 1 plus 3t, and the other equate 2 equals 2 plus 2t. And then we got 2 plus x equals 2 plus 6s, and y is equal to 3 plus 4s. Here are our parametric equations, and since the x's are equal, we can say that 1 plus 3t is equal to 2 plus 6s, and the other one that 2 plus 2t is equal to 3 plus 4s. And you've got another system of equations with t and s that if you wanted to solve, you could use matrices, you could use substitution, you could use elimination, whatever you would like. Okay? If you chose to use elimination, I would probably multiply this equation by 2 and this equation by -3. That would cause my t's to cancel out. What would I get as a result? I would get 2 plus 6t equals 4 plus 12s, and -6 minus 6t equals -9 minus 12s. And when I add these equations up, I get -4 is equal to -5. Who knew? Interesting properties of negative numbers. No, that is not true, and so this is not possible and therefore the lines have to be parallel. Now, obviously, the first method is a better method for showing that they're parallel because it's simpler and easier. But let's say you did this and we're trying to solve for the intersection and you got something weird like this. It's important to see that to know, oh, that's okay that it's weird. It just means that these two lines were parallel right from the beginning and that they never intersect. If we got 0 equals 0, they'd still be parallel, but they'd be the exact same line, and they'd always intersect. So both of those situations would be parallel lines, one where they never intersect and one where the parallel lines are exactly the same. This is the most common in 2 dimensions. You just have to have the slopes different, and in 2 dimensions, those lines will cross. How do you find out if they cross? Well, you set up your systems of equations and solve, and you'll be able to solve for both S and for T, and it will allow you to plug it in to find that point of intersection. So you'll notice in these questions that we set up our parametric equations for both lines. So here's my first line. There's my second line. And with your parametric equations set up, if they intersect, the x-coordinates would be the same, the y-coordinates would be the same, so we can do a little substitution here and get -3 plus t is equal to 4 plus 3s, and 5 plus 2t is equal to 3 minus 2s. And again, you could choose to solve this with matrices, substitution, elimination, whatever you would like. Okay? I think my favorite is elimination. So I often take that first equation, I'll multiply everything by -2. And you just have to be careful not to make any mental math mistakes. It's sometimes easier said than done. So I eliminated the value of t. That allowed me to solve for s. Once I've solved for s, I could plug that back into an equation and solve for t. So for example, in this first equation here, if I now plug in s is -2, I will get t is equal to 1. It's sometimes good to also solve for t, because this is your way of checking if you got your question right. Go back to your original equations. If t is equal to 1, then the vector r would be -3 plus 1, -2, 5 plus 2, 7. And if s was -2, and I plug that into this equation, I also get -2, and I also get 7. So finding both s and t and plugging it in allows you to check, did it actually work, right? If you like to live on the edge, just cross your fingers. You could have just solved for s, just plugged it into R2, got your point and said, I am confident that I never make any mental math mistakes at all, and I'm just going to leave it without checking anything over. So we can write a statement. We can say that for sure we know that they're concurrent since they intersect at -2, 7. And in 2 dimensions, the final thing is that they are exactly the same line. They have an infinite amount of solutions because they always intersect when they're the same line. Everything works. So we again set up our system of equations. If we try to solve for where they intersect and we get a thing that's always true, like 5 equals 5, then you know that it always works and they'll be the same line. Okay? Sometimes in vectors it's not easy to see that they're the same line. Because, like, I hope you can see the slopes or the direction vectors are parallel, because you could just take the top one and multiply it by 2 to get the bottom one. But they have different points. So again, when we set up our parametric equations, from our first equation and from our second equation, multiply equation 1 by 2, take equation 2 and multiply by -3. Strategically make no mental math mistakes. Add your equations up. And you get the statement that -4 plus 0 happens to also equal -4 plus 0, which is always true. Therefore, these are coincident lines. Okay? If on your test you say they are the same line, I'm okay with that. You don't have to use the fancy word that these 2 lines intersect at one point, which is what they do. I'm okay with that. Now, when we get to 3 dimensions, you can have 2 things that aren't parallel, but still don't intersect, right? You make all sorts of lines that don't intersect. Like you imagine 2 planes flying, and they leave their little vapor trails. They can be going in different directions and not intersect. And the vapor trails can intersect, and you can still be okay as long as they intersect at different times. That's okay as well. The problem is when 2 planes happen to intersect at the same place at the same time, that's not as good. Ooh. Anybody know what Greek letter this is? Yes? No? What is it? It is lambda. Yes. Okay. This one's boring. That one's kind of boring too. Let's do a 3-dimension one. And then I'll give you time to work. You can try the other 2 boring ones that are in 2 dimensions. But let's do one that's 3 dimensions and find out, do they intersect? Or are these skew lines? Or are they parallel? What's happening? So again, we'll always, when trying to find intersections, we'll go to our parametric equations. So in line 1, we would have 2 plus t. Y would be 1 minus t. And z would be just t. Our second equation would have x equal to 3 plus 2s, y would equal to 3s, and z would equal to negative 1 minus s. I like to write them beside each other like this, and then take equation 1 and say, from there, I can make the following equation. 2 plus t is equal to 3 plus 2s. And from the second one, I can say that 1 minus t is equal to 3s. And from the third one, I can say that t is equal to negative 1 minus s. Notice the green equations have only two unknowns. You don't know s, and you don't know t. How many equations do you need to solve for two unknowns? You only need two equations. So I could choose equation 1 and 2, or 2 and 3, or 1 and 3 to solve for s and t. Okay, it wouldn't matter which ones. I really think substitution would work nice here because you've already got t by itself, or elimination would work really nice because you could just add equation 1 and 2 or equation 2 and 3 together and things would cancel out. Can you see how adding equations together things would cancel out nicely? Okay, but since we haven't used substitution yet, I'm going to take equation 3 and I'm going to substitute it into equation 2. So I just took the t, replaced it with negative 1 minus s. I have to distribute my negative sign. 1 plus 1 will be 2 plus s equals 3s. 2 is equal to 2s, and s is equal to 1. Okay? What did I do? I was using, just going to make a note here, that I was using 2 and 3. So when s is equal to 1, can you see that t, if I plug s as 1 in here, t would be negative 2. And that will work for both equation 2 and equation 3 for sure, because those are the equations I use to solve. But there's going to be some times in 3 dimensions that you solve equation 2 and equation 3, you also need to check, does it also work for equation 1? Or you have to plug in those values into the original equation and see, are the points actually the same? So in this situation, can you see that if I plug in negative 2 for t and 1 for s, this doesn't work, does it? And if we try to plug it into the original equation, okay, notice if I plug in t is negative 2, the point that I get is 0, 3, t is negative 2. And for line 2, if I plug in s is equal to 1, I'm going to get 5, 3, and negative 2. They were so close, I got the two parts of the coordinates to be the same, but not the third one. These lines are skew lines. Right? They're not parallel because we can't just multiply this one by 2 and get this one. But they don't intersect. So you have to be careful because When solving a system of equations, yes, you only need 2 equations and 2 unknowns to solve. But if you have a third equation that it also has to work, you have to check, does that work in that third equation as well? So a couple of ways that you can check, right? I made sure that I was working with 2 and 3, only working with 2 and 3, and I solved for t is 2, t is -2, and s is 1, and I checked, and yes, it worked for both equations 2 and 3, which means at least I didn't make a mental math mistake. If it didn't work for 2 and 3, that just means you made a mental math mistake. Because solving a system of equations when you have 2 things and 2 unknowns, there's either a solution, or there are infinite solutions, or there's parallel lines. But then I had to check that it worked in the first one. The other option is you could find your answers and plug it back into the original equation and see, are the points actually the same? And they should be the same for equations 2 and 3 because those are the ones you used, but unfortunately in this case, it wasn't the same for the first one. And so what do we know from that? These never intersect.